In this video, we're going to look at the relationship between graphs and their derivatives. So we've got a graph, y equals f of x. I'm going to use the analogy which is close to my heart, Istanbul. In Istanbul, we have got a lot of hills, so I'm going to use the analogy of walking up and down hills. So let's look at what we've got. We've got a function. If we start at this point, we're walking up a hill, we get to a level part, then we go back up the hill, we reach the top of the hill, then we start coming down, 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 all the way down until we get to the bottom of the valley, and then we start going up a very steep hill again. The first thing I want to look at is the first derivative. So remember that the first derivative is a measure of the gradient of a graph. So what is the first derivative along this point? Well, because along this point the graph is an increasing function, in other words, f of x is getting larger as we go along this part of the graph, we can say that the gradient along this point, f dash of x, is positive, so it is greater than 0. If anywhere along this point we were to draw a tangent to the graph, so let's draw a quick tangent. As you can see, the tangent at this point is positive. Again, if we draw a tangent here, the tangent to the graph is positive. So we can say that along any part of that graph, f dash of s is greater than 0. So I keep going up the hill and I get to this point here, which is flat, but it's not a maximum or a minimum, but at this exact point here, the first derivative is 0. It is a flat point on my analogy. I've gone up the hill and got to a flat point where I have no gradient. So at this point, f dash of x is equal to 0. Then I keep going up the hill, up the hill, up the hill, up the hill until I get here, where again, for one instant, the gradient is 0. I have a flat point, and this is a maximum, sometimes called a local maximum. So at this point here, as you can see, if I draw a tangent, the gradient is 0. So again, f dash of x is equal to 0. Then I go over the top of the hill, all the way down, down the hill, down the hill. My gradient is negative, is negative, is negative, is negative, until I get to the bottom of the hill, where again, for an absolute instant at this point here, f dash of x is again equal to 0. This is called a minimum point. If I draw a tangent again, you can see that it has no gradient. And then I start going back up the hill, up the hill, up the hill, up the hill. It's an increasing function. So at this point of the graph, the gradient is positive. So f dash of x is greater than 0 here, and at around this point here, f dash of x is less than 0. So let's summarize that. We've got a positive gradient greater than 0, then we reach this point and the gradient is 0, then it carries on, it's positive until it reaches this point here, which is a maximum, and the gradient is 0. Then we go down the hill all the way where the gradient is less than 0 or negative. Then we reach the bottom where the gradient is again equal to 0 at the minimum, and then we go all the way back up the hill and the gradient is positive. The second thing I want to look at is the second derivative, and remember that the second derivative is a rate of change of gradient. In other words, how is the gradient changing along a function? So if we look at this part of the function, the first derivative is positive, and we've already discussed, but how is it changing? If we're walking up a hill, what is our gradient doing? Well, at this point, it's very steep. It's very steep, very steep. It starts to get less steep, less steep, less steep, less steep, until the gradient becomes 0. And it's easier to see if we draw in some tangents. So if we draw a tangent here, it is positive, but very positive. If we draw one here, it's still positive, but less positive. If we draw one here, it's positive, but less positive. And like we've discussed, when we get to this point here, the tangent has a gradient of 0. And because it's got a gradient of 0, it is called a stationary point. But this point also is a special stationary point. It is also a point of inflection. Point of inflection. And POI. So the gradient up to the point of inflection is getting less. So we call that it's getting less and easier. So we call that concave down. After the stationary point, the point of inflection, the gradient starts to get steeper and steeper and steeper and steeper and steeper and then gets to a point here, and then starts to get easier again until it becomes 0. And that is another stationary point, and that is a maximum. And then again, the gradient becomes negative, but it gets easier and easier going down the hill, gets easier and easier. The gradient is still negative, and it's getting more negative, and it gets easier and easier and easier until we reach that point, which is again another point of inflection. And then after the point of inflection, it starts getting harder, still negative, but it's getting less negative, less negative, less negative until we reach that point, which is a stationary point, and that is a minimum. And then again, it becomes positive. It gets harder and harder and harder and harder and harder and harder until we reach a point around there or there. We can't actually tell whether at some point up here there'll be another point of inflection, and walking up the hill will start to get easier. I'm going to put some vertical lines where these points of inflection are. So I've got one here. I've got one here. I have a point of inflection there. and as we go up the hill, there'll be some point of inflection, but I don't know how steep that gradient is, so I'm going to leave that one out. So now let's see what we have in terms of second derivative. Well, this point here, it's getting easier. The gradient of the graph is getting less and less and less until it becomes zero. That means that the rate of change of the gradient, or the second derivative, because it is getting less, it is negative. So the second derivative at this point, f double dash of x, is less than 0. In these 2 points, the rate of change of the gradient is increasing, so we say that f double dash, the second derivative, is positive. Again, between these 2 points, it's increasing, it's still getting easier and easier and easier until we get to that point. So this again, the second derivative, f double dash of x, is less than 0, and then after this it gets harder and harder and harder until we get there, and it starts to get harder and harder and harder again. So again, f double dash, the second derivative, f double dash of x is greater than 0. So we also can say when f double dash of x is less than 0, it is concave down. The rate of change of the gradient is getting easier. And when the second derivative is positive, so the rate of change is increasing, we say it is concave up. And a point of inflection, like this point here, is where the concavity changes from, in this case, concave down to concave up. Here, this point of inflection, concave down to concave up. This point here is a very special point of inflection. It is a stationary point of inflection because at this point here, the first derivative is 0 and there is a change in concavity from concave down to concave up.